Hello, everyone. My name is Dr. Clement Chumesi. I'm a medical statistician for the Norfolk Department of Medicine at the University of Oxford. So this particular YouTube video you're watching is part of a master class that I did for the National Union of Ghanaian Students in China. But it is open for everyone to watch and learn at their own pace. So please, if you are watching any other part apart from part one, don't forget to watch the previous part. So if you are watching part two, please watch part one and part two before you watch part three. If you are watching part two, please don't forget to watch the first part or first session before you proceed. Okay, so thank you very much, and I hope you enjoy the video. And please don't forget to subscribe. Your subscription is much really appreciated, and it is one way of supporting us, and we really appreciate it. Thank you very much. Enjoy. Cheers.
Okay, so in a few minutes, I'll take questions before we continue. So the next one is about dimension reduction techniques. Now, I was also supposed to talk about variable selection techniques. Okay, I was also supposed to talk about variable selection techniques. Variable selection techniques. Unfortunately, many people confuse dimension reduction techniques with variable selection techniques. So variable selection techniques is situations where you have so many predictors. Okay, most people who don't work with large data sets, they often don't have that problem. But those who are dealing with observational studies, let's say you went into the health records and then you were interested in some study, and then in the UK we have certain database for health data. Example is Biobank, and then we have the CPRD database and all that. So there are so many. It means the data, hospital data. We have database. I think Ghana, they have something they call the DIMS and so on and so forth. So there are so many databases there. So situations where you want to now take a certain data, secondary data, and do your analysis, but you notice that there are several information that has been collected for each patient. Do you put all those variables as predictors of a certain outcome in the model? Remember that there's a certain problem that I needed to tell you. We call it multicollinearity. In as much as we want to see possibly, it means a regression model will do well if the predictors have high effect or high relationship on the outcome. So it means that situations where the predictors have low relationship or association with the outcome, okay, then it means that regression model will not be the very best. Okay, maybe it means that there are certain variable transformations or there are better models you should consider for such instances, possibly due to violations in some parametric assumptions and so on. Fine. So what we do is that, so that's basically that for the case of regression. So we are just looking at, we want to see high correlation between the predictors, high correlation between the predictors and the outcome. But we don't want to see high correlation among or between the predictors. So it means the predictors, let's say if you have 10 predictors in the same model, that is how come you fit a model and the model failed to converge, or the regression estimates are abnormal and it doesn't make sense. It's because there are high correlation among the predictors. And that introduces a problem called multicollinearity. Multicollinearity is a statistical problem we want to avoid. It means that we don't want to see high correlation among what? The predictors. When it happens that way, this is what happens. So one, if the regression model is significant, it means that at least one of the predictors is supposed to be significant. However, in the presence of multicollinearity, a model can be overall significant, but none of the predictors was significant, and vice versa. Vice versa means that if none of the predictors is significant, we also expect the overall model not to be significant. But in the presence of multicollinearity, this also happens. And sometimes the model fails to converge. Okay, fails to converge, or the estimates are abnormal. Okay, so basically it means in the presence of multicollinearity, you cannot trust your regression estimate. So how then do we deal with it? So that brings us to what we call variable selection techniques. So variable selection techniques are ways of selecting the most influential subset of candidates, candidate predictors, or are ways of selecting subset of those numerous predictors so that we can improve model fit. Okay. but not all the variable selection techniques are able to deal with multicollinearity. So there are standard variable selection techniques that do not deal with multicollinearity. A perfect example is stepwise, the stepwise forward and backward elimination selection. Okay, so that's like, so in R, if you fit a regression model and then you just type step of the model, it will do stepwise regression. So the stepwise regression means it will consider different possible combinations of the predictors, and at each stage evaluate something called the AIC. The AIC is archaic information criterion, and the archaic information criterion is used for selecting the best model. So it means if you fit different models of the same kind, and you want to know which model was the best, the model with the least AIC statistic is the best model. Fine. So what the stepwise regression does is that it fits range different models based on different selection of predictors in a stepwise fashion, just like the stepwise, the hierarchical stepwise regression I was trying to explain. It does that in a stepwise fashion. And then the last one is always the best because that had the least AIC. Fine. Now, and there's also another one called BIC. So either AIC or BIC. AIC is archaic information criterion, and BIC is Bayesian information criterion. The smaller the value for a particular model, the better. The AIC or BIC would be meaningless if it is only one variable you've actually what? It is only one model you fitted. The AIC or BIC is meaningful when you have fitted different models of the same kind. The emphasis is of the same kind. So don't go and look at AIC of, let's say, a regression model and compare it with AIC of a certain different model, which is not a regression model, and tell me that the model with the least AIC is the best. No. If you are comparing different models, so for instance, if I want to compare machine learning with classical regression methods like the GLMs or the general linear models with, let's say, random forest, I cannot find AIC. As a matter of fact, I cannot even find AIC for the machine learning techniques. Okay, so in that case, we need a performance metric. An example of such performance metric is like accuracy measures, okay? Or you could use error statistics like mean square error, mean absolute percentage error, and mean square, mean absolute deviations for situations where the dependent variable was continuous. And then if the dependent variable was categorical, then you can use percentage accuracy. Okay, and to do that, we often split the data set into training set and testing sets. So you fit the model based on the training set, which should be large enough. And then the testing set is used for cross-validation. By cross-validation means that we will try and predict the outcome on the testing set, the data we left out, and check the proportion or the percentage of times that the predicted classification was equal to the observed or the true classification. And the proportion of times we made the correct classification is called accuracy, percentage accuracy. And that, in that case, is a way to compare different types of models for classification problems, right? So if I want to compare, let's say, random forest or classification tree or gradient boosting machines with, let's say, a logistic regression, then I should rather be comparing their percentage accuracy, not AIC. Okay, so AIC is used to compare models of the same kind, and not every model you can evaluate their AIC. To evaluate AIC, you need to know the likelihood function. You don't need to understand what I mean by the likelihood function, but not every model can have its likelihood function explicitly written. And so that's why machine learning techniques, you can't find AIC because AIC is a function of the likelihood. I mean, if you go online and you type AIC statistics, not now, AIC statistics, so you notice that it is a function of the likelihood function, and not every model not every model that has its likelihood function explicitly evaluated or could be written. Okay, so that's why it's not applicable to all class of models. Fine. So variable selection techniques is just to select subset of predictors that we believe would that we believe would improve model fit. And so one example is we have the recursive feature selection, and we have machine learning techniques also for variable selection. So for instance, we have the brutal, we have even specific machine learning selections that are based on classification to random forest, gradient boosting machines, and so on. We even have simulated annealing techniques and so on. So there are many methods in that case. But the moment you want to now account for multicollinearity, then you use something called penalized regression techniques, like ridge regression, lasso regression, and something called elastic net. So by ridge regression, what we are saying is that, let's say if you have 20 predictors and you want to know which subset of the predictors is the most influential, at the same time accounting for multicollinearity. So what we do is that ridge regression, what it does is that all those all those predictors that are less important, it will set their weight of importance or their regression estimate to something close to zero. Not zero, but close enough to zero. If it is close to zero, okay, then it's just trying to say that it's not important. Then the ones that are farther from zero, okay, so, or the ones with high weight of importance, they are the predictors of high importance. So it means ridge regression is technically not a variable selection. It doesn't necessarily select variables. It allows all the predictors in the model, but it penalizes all those variables that are less important to have a very insignificant regression estimate. And if they are insignificant regression estimate, then it means that it is automatically favoring those predictors of high importance. But a much more brute force or a much more brute version is what we call the lasso regression. So the ridge regression is also known as L2 regularization. So in case you hear of L2 regularization, it's the same thing as the ridge regression. But the lasso regression is also known as L1 regularization. And what the lasso does is that, unlike ridge regression, certain variables of less importance to have a weight of importance close to zero, what lasso regression rather does is that all those predictors, if there are 20 predictors, all those predictors out of the 20 that are not important, it will set the weight of importance or its regression estimate to zero. It will set it to zero, not close to zero, but to zero. To zero means that there could be 10 predictors and only 3 of them had non-zero weight or non-zero estimate. Then it means all the ones with zero estimate, take them out. And the ones that have non-zero estimate, first of all, are the most influential predictors. And at the same time, they are free from multicollinearity. So that's the beauty about the lasso regression. And the elastic net combines these two. So the elastic net combines ridge and lasso regularization or regression together. So it means the elastic net is an L1 and L2 regularization technique. So it means it's applying. So it means some variables would have their weight of importance set close to zero. Some will be set to zero, and some will be having high weights. So that's the elastic net. But the truth is that if it's about selecting the subset of variables that are more important, then the lasso becomes the best option. All right. So that's something I wanted you to understand. So that is different from dimension reduction. Those who do proteomics data analysis, genomic data analysis, like situations where the kind of data used is quite heavy. By heavy means high dimensional. What happens is that with the dimension reduction technique, example, principal component analysis. Principal component analysis help us to, first of all, kind of combine all those variables into just one. Okay, so it means that, let's say if there are 20 or 300 protein samples, it's combining all of them into one, so that the first principal component will be a linear combination of all those variables. And then principal component 2 will be a linear combination of all those variables after taking one out. Principal component 3 will be a linear combination of all those variables after taking 2 out, in that fashion. So it means that one thing about principal component analysis is that it converts your data by combining the data in such a way that you have something called principal components. And the principal component, we believe, not that we believe, explains the variability in the data than any individual variable. Okay, so it means that people can even combine data set into principal component and use the principal component as a predictor in a regression model. So it means if it is a logistic regression model and then you've added some of the predictors, it's a principal component, you call that logistic model as a principal component logistic regression. So it means anytime you hear principal component attached to any regression model, it means it's a classical regression model, but at least one of the predictors is a principal component. Okay, so remember that principal component can be used for many purposes. Apart from the fact that we are able to use it to reduce the dimension, it also helps us to know variables we could take out. So it means that, let's say if you consider the first principal component, which explains most of the variability in the data than any other variable and also than any other principal component. It means if you look at the relationship between each variable and then the principal component through something called communalities, I don't expect you to understand this. I would have a whole video on YouTube on principal component. Yeah. Today I even thought of considering that as the practice task, but I felt it to be too advanced for some people. So I just wanted to consider something a bit simple. But I don't want to. I mean, I was going to show you an instance of it, but it feels like it's a work in progress yet, so I wouldn't want to share that yet. Yeah, but I'll do a whole video on that. Fine. So with principal component, the first principal component, for instance, okay, if you should look at the relationship of each of the predictors, okay, or the variables that you use to perform the principal component analysis, okay, the variables that have less correlation with that principal component, it means that those variables should be what? It's not important or can be taken out. So the question is, how many variables should you take out? So it means that if there are 20, let's say, variables that you use for the principal component analysis, remember when you're doing principal component, you don't include the dependent variable. And principal component analysis are applied to only numeric data. Principal component analysis are applied to only numeric data. Situations where all the data sets are categorical, then we have something called factor analysis. So factor analysis is the twin brother of principal component analysis, just that it is applied to categorical data sets. Okay. So it means that in certain softwares like SPSS, they always confuse principal component with factor analysis. They make it behave as if it's the same. It's not the same, but the principles are the same. But the area of application or the kind of data you use is different. Okay, fine. So it means that for the principal component, let's say if there are 20 variables you use for the principal component, it will generate 20 different principal components. If you use 20 variables for the principal component analysis, it will generate 20 different principal components, where the first principal component is a linear combination of all the variables without taking anything out. The second principal component is a linear combination of all the variables after taking one out. The last principal component, which is in this case the 20th principal component, will be a linear combination of all the variables after taking 19 of the variables out. Now, for each of the principal components, there's something called the eigenvalues, and the eigenvalues quantifies the variance. Okay, that is explained by each principal component. The moment the eigenvalue is just above 1, meaning that all those principal components where the eigenvalues are below 1, they should be discarded. Okay, they must be discarded. So imagine if the eigenvalue for each of the principal components, the first one would always have the highest eigenvalue or the variance. So imagine if it gets to the 4th principal component, when it was getting to the 5th, the eigenvalue or the variance was just below 1. Then in that case, it means you should end at where the eigenvalue was just above 1. So if where you are ending is principal component 4, principal component 4 means that a linear combination of all the predictors after taking 3 of the variables out. So if you want to now know the variables you should take out, then you go back to let's say the principal component 1 and 2 or 1 and check all the predictors, which of the last 3 has, or which 3 of those variables has the least association with that principal component. And it means that those variables can be taken out. And that association is actually obtained by something called communalities. And the communalities is just a sum of something called factor loadings. You don't need to understand all these, but there are things that you can easily do. And there are a lot of online information for that. So some of you might be doing certain kind of analysis and you might need to apply principal component. So it means principal component can help you also for variable selection, okay? And it also can account for multicollinearity. The reason is because the principal component, there's no correlation between the principal component. So it means that even though the original variables had high correlation between them, converting it to principal component, then the principal component do not have high correlation between them. So indirectly, the principal component added as a predictor will be free from multicollinearity. Okay, but how do we interpret it? I think I'll have a whole video session on that. And one can also use principal component analysis like a clustering analysis. although we have set of statistical methods called cluster analysis, they exist. Okay, they are set of. So if you want to know what I mean by cluster analysis, let me see. Just a minute. And don't get scared. I just want you to see how it looks like. Just a minute. So it's like you have a data and we've been able to stratify the data into separate clusters. But we can look at a 3D version and you can see something like this. Okay, so this is what I mean by cluster analysis. It's like we're trying to find distinct patterns in the data set. Okay, fine. But when it comes to principal component analysis, if you look at if you look at the scatter plot of principal component 1 and 2, sometimes it helps you to identify potential clusters that exist. So one example is, I think, in one of my papers, okay, this one, just a minute. Okay. This paper is very mathematically heavy, so don't, yeah, I just want to explain. Yes. So for instance, if you look at this one, just plotting the principal component 1 and 2 helps me to identify patterns that exist between the data set in a reduced dimensional space. Another example is let me just, so I have a whole code on principal component analysis, just that I was using it to a certain data set, which is like for an actual study that is yet to be published. But I'm just trying to let you see how, yes. So for instance, let's say I have a data set and the data set is on proteins. So it's like a proteomic data set. And we are and then the data was collected based on some specific materials. And then we wanted to compare whether there's any pattern in the protein expression between those two materials, in this case, plasma and serum. So here it's telling us that the protein expression levels in the plasma material was higher relatively than those in the serum. And that is how beautiful sometimes, or that's how beautiful you can also use principal component analysis to visualize that. So I would say that principal component analysis is multi-purpose. One could automatically use it to aid in variable selection. One could use it to reduce the dimension of the data and include those principal components as predictors in a model. And secondly, or thirdly, one could also use it to visualize patterns that exist in the data. But if you use it as in a regression model, okay, if you use it in a regression model, the beauty is that if I come down here, just a minute. So for instance, I use it as a regression model and included them as predictors, right? But before then, I had to also identify which subset of the predictors I should consider. So it meant that I first of all eliminated all those principal components whose eigenvalues are less than 1. Okay, because if there's less than 1, it means that those variables must be automatically discarded. And the ones that are not discarded, I also applied stepwise regression to select the best subset. So this is what I mean by stepwise regression. So it's like you have a regression model of all your predictors. So in this case, I'm doing it to just the principal component. And then it does, so at each stage, it is now reducing the dimension and it is finding a separate AIC. And then it does that till it gets to the last phase where it tells me that if I should consider a model where these principal components are the predictors, then that will be the best model. Okay. And yeah, so in that case, we went further fine. Going through that process, okay, going through that process helped me to get a model that is, where is it? Just a minute. Help me to get a model that is 81% accurate. And at the same time, so if you use the principal components as predictors, so for instance, these were the best predictors of the principal component, for instance, and you can select which of the protein samples that actually has significant contribution to those principal component you use as predictors, so that it will help you. So it means that if you combine the how do you call it? If you use PCA to combine the data set, it doesn't throw away the information. As a matter of fact, you'll be able to identify which set of protein samples or which set of variables actually do well or perform better on those principal components that you considered as predictors in the model. So that's just something I wanted you to note. Fine. Okay, so that's all about dimension reduction with principal component. There are other methods. I don't want to go up to that because of time. And for time series analysis is basically where your data is collected over time. Okay, so it means situations where data is collected over time. Sometimes it can just be a single data set. So if you are looking at GDPs, let's say inflation rate over time, that is a typical example of what a time series data. But the moment I decide to collect several time series data sets, like let's say exchange rate data set over time, GDP over time, monetary policy rate over time, let's say inflation rate over time, then I have a multivariate time series data. But the moment this multivariate time series data is collected for different countries, then it becomes a panel data. And that panel data can also be seen as a longitudinal data set. The reason is because longitudinal means you combine a cross-sectional data, cross-sectional because several variables now, and collected over time. Okay, so but that's a typical example of what I mean by a panel data. Yeah, but panel data sets are different from hierarchical data sets. So longitudinal is a more generalization, but remember, like I said, a data can be hierarchical but not longitudinal, and a data can be hierarchical and longitudinal at the same time. Yeah, I think I've explained that. So and the time series models too, we have different versions, and we have machine learning based time series models. Like my paper, the paper I was talking about, I mean, the previous paper on the machine learning. Yeah. So that is just to say that machine learning techniques, we have different methods depending on the kind of data set. Okay, fine. And then there's something that even top statisticians are not aware of. We call it functional data analysis. And functional data analysis is something that most people remember, like even top I mean, I think in my postdoc, I asked my supervisor, like my supervisor in Oxford, that have you heard of functional data? He said, no, this is the first time. Yeah. So it's just to say that many people are not aware of, even top statisticians. So if you don't know, that's not a problem. But functional data analysis is like, it's a new data kind of analysis. Okay. Where for any data set, the cross-sectional data set, the longitudinal data set will be here. But remember, it is applied to longitudinal data only. So if a data is cross-sectional, you can apply functional data analysis on it. So functional data analysis is a new statistical method where it converts data into curves. By converting data into curves means that it converts data in the real space to something called Hilbert space. In the Hilbert space, data is now converted to curves. So it means that situations where you are trying to look at the rate of change, maybe there were instances where trying to predict the change in some outcome. Okay, you are looking at the change from baseline, let's say a certain future time from baseline and everything. The beauty about functional data analysis is that if those of us who have done pure mathematics before, or if you've done even elective mathematics at secondary school level, I'm sure at secondary school level you were exposed to differentiation, right? Now you should know by now that the first differential is equivalent to the rate of change. Okay, and if you look at even speed, velocity, and acceleration, if you differentiate distance, you get velocity. If you differentiate velocity, you get acceleration, and so on. Fine. So one thing is that you can convert data into into the. I actually used this method in a competition in the UK. So it was basically a competition organized by Innovate UK. So it's more like the board is like the government body that is interested in advancing research and trying to, integrate or somehow help academicians to collaborate with industry. So it means that people from the industry bring their problems, and then we will use our advanced statistical methods to solve those problems within 3 days, and they would take care of as our I mean, in terms of how do you call it, where you sleep and everything. So maybe those times I was in Cardiff, and maybe they will be organized. They organized the first one in Cardiff, and the next one I think I went for it at Manchester University. So it means that you go to a certain university, they cater for your accommodation and everything, your feeding, everything, and the goal is within 3 days apply advanced statistical methods to solve industrial problems. And I use this functional data analysis to make it easier for you to understand this. An application of this was, so there was a big data from the US, and then the data was based on orthopedic surgery. So it's more like orthopedic surgery, and they've collected certain information about the bone at different body location, and they were more like the main outcomes. And then they were trying to now look at certain predictors, how they predict that. But more importantly, they noticed that anytime they treat a patient, okay, like let's say someone is suffering from a bone-related infection, they could treat the patient, and after a certain period of time, it feels as if the patient has recovered in such a way that the values, those performance metric from the data, so it's like there are certain outcomes or primary endpoint that they use to conclude how well the patient is doing. And they notice that those performance metric remains constant. As a matter of fact, it remains constant as if the patient is not suffering from any pain. And then after a certain period of time, there is a relapse, and then the patient suffers for the pain. Gets the pain actually relapse again. But the question is, they didn't know how long that remission period is, how long that an individual remains appears to be free from the pains for a period of time. They don't know. How can we learn that based on the population data set? So what I did, and it was a smart thing I did, and ever since I developed a good relationship with the team, and I'm even one of the data scientists for that company, and was that I used the functional data analysis to do that. And the first thing I did was I converted the data set into curves. And the data set is a longitudinal data set. So converting it to curves means that I've converted it from the real space to Hilbert space. And after doing that, now in the curves, the data now is like a function. So just imagine if you consider a particular individual data over time, you've converted that data into a function that is differentiable. So it means if I want to know the rate of change, I can differentiate that data, and the first derivative is like the rate of change. And imagine if you now plot the rate of change across all the patients, and then you notice that there's a certain period where the rate of change was zero. You know, when the rate of change is zero, it means that that data was not changing over time. So it means that I was able to get a visualization such that the data was changing, and it got to a certain point, the rate of change was zero up to a certain point, and then the rate of change, and then the rate of change was non-zero anymore. So I was able to know exactly for how long the rate of change remains zero, and by so doing, I was able to tell how long an individual can undergo remission. That is, feel like they are free of or have recovered from the pains, and how long it takes. I was able to tell that from the functional data analysis. So it's just a simple application of the functional data analysis. And there's another one called network analysis. Network analysis is very important. And there are different types of network analysis. Even those in political science, you have there's a certain network analysis, the analysis called the discourse network analysis or something. And it's also used by those in political science to check how different opinions of politicians agree with each other. And there are other performance of agreement or metric of agreement. So we have intra-class correlation, we have kappa statistics also there. But the network analysis is just a way to visualize relationship between, let's say, certain outcomes of interest in the graphical structure. Okay, so one example, one perfect way where I applied network analysis was during my MPhil. So my MPhil research, I did it in Ghana, which was predicting it was using something called Markov chain modeling of HIV, tuberculosis, hepatitis B transmission. In 2018, it won the best research in Ghana at the master's level. And so let me see. Okay, this is one of the publications from it. And so from here, let's see how network analysis was employed. Okay, so let me just download this one. Okay, all right. So for instance, we know that if so I was looking at HIV, tuberculosis, hepatitis B. So there were two publications from the paper. The work was like MPhil, but was done like a PhD, such that when you go to Google Scholar and you type the research work, it's treated as a PhD work. If you go to Google Scholar and you type the topic Markov chain modeling of HIV, tuberculosis, hepatitis B, yeah, it's treated like as if it was a PhD work. Fine. So where's the PDF? Just a minute. Okay, yeah. So just a minute. So here, so for instance, one way of applying network model is so for instance, HIV, tuberculosis, hepatitis B. We do believe that if an individual is suffering from HIV, one of the first tests they do is to check whether the individual has tuberculosis. Because for every 4 individuals with HIV, we believe that one of them has tuberculosis. So it means if someone is suffering from tuberculosis, there's a chance that that person could have HIV. It's not always the case. But we are just trying to say that HIV, the leading cause of death among HIV patients is tuberculosis. So it means there's some kind of link or association between HIV prevalence and tuberculosis incidence, right? But we didn't know whether there's relationship between HIV and hepatitis B or hepatitis B and tuberculosis. We didn't know. And remember, for HIV, it's not really an infection necessarily. What HIV does is that after your immune system is compromised, it allows other infection called opportunistic infection to fight for or compete for the health of that individual. So it means it destroys your immune system such that several other diseases can now occur in that individual, right? But we didn't know whether hepatitis B was one of them. And we didn't know whether if an individual has HIV, there's a chance that the person could suffer from hepatitis B. So one of the ways for me to visualize that was to use something called Bayesian network or directed acyclic graphs. So this one means like I used a network analysis to check whether there is going to be a relationship between them. You can see that there's a relationship from HIV to tuberculosis. There's no arrow joining hepatitis B to HIV or hepatitis B to TB. It is only joining HIV to TB. This is and then you notice that it is coming from HIV, not TB towards HIV. So this is to say that we are not saying that people with HIV would have people with tuberculosis will have a high chance of HIV. We are rather saying that those with HIV, there's a high chance that they will have tuberculosis. Okay, so this is just to say that we can use network analysis to visualize complex associations in a graphical fashion, okay, or in a network fashion. So in that case, there's something called nodes, okay, and then relationship associations are represented by those arrows, and the arrows are called edges. Okay, fine. And there are so many models, and time might not permit us. But the only thing maybe I'll talk about now is the robust regression methods. I've already talked about Lasso, Ridge, and Elastic Net, right? You can use them as a regression, and you can also use them for variable selection. As I said, Ridge is not the best for variable selection because, like I said, it sets variables of low importance to a weight of something close to 0, but not 0. The Lasso is a bit brutal, and it means that if you want to now know the best subset of most influential predictors, okay, whilst eliminating all those that are not important, then Lasso becomes the alternative. But there's something called quantile regression. I think I'll just talk about this and end for the first phase. Yeah, I'm sure everyone is tired by now. Now, quantile regression, many people probably might not be familiar with, and many people don't know that most of their research that they've been doing, they actually need to use quantile regression, just that they didn't know. So all the GLMs, the generalized linear mixed models, the generalized linear models that we've been talking about, remember they predict the expected values or the mean of the data. They predict the means. And if you have probably been in an elementary statistics class, you notice that whenever there are outliers is where we have extremely large or extremely small data, okay, or values in the data. And statistically, an outlier is situations where, let's say if you pick a variable, you find a mean, and then you find a standard deviation. Then you construct this range, the mean minus 3 times the standard deviation as the lower limit, and then the mean plus 3 times the standard deviation as the upper limit. That range, okay, is one way of concluding whether any data point is an outlier or not. Any data point that falls within that range is not an outlier, but any data point that falls outside that range is an outlier. And if it falls outside that standard deviation, what we mean is that any data point that falls outside 3 standard deviations of the mean is an outlier. So that's the statistical definition of an outlier. But remember that outliers, there are two things that will not make a data to be normally distributed. So mostly when the data is not normally distributed, we conclude that because they are outliers. It's not always the case. A data can be free from outliers. So like I said, the range 3 times the standard deviation minus the standard deviation minus 3 times the standard deviation. Oh, sorry. The mean minus 3 times the standard deviation as the lower limit, and the mean plus 3 times standard deviation as the upper limit, in order to define an outlier. There are instances where bulk of the data falls 3 standard deviations above the mean. That is right skewed. And there are instances where bulk of the data set falls 3 standard deviations below the mean. That is left skewed, even though they are still within the range. So this is to say that a data can be either positively or negatively skewed, but has no outliers. And when a data, so it means that there are two sources of non-normality. A data can be non-normal, not because of only outliers, but because of skewness. But remember that when a data is non-normal because of outliers, the certain data transformation like logarithmic transformation can maybe convert the data to be normally distributed. But when the non-normality is due to skewness, whether left skewed or right skewed, no amount of transformation will convert the data to be normally distributed. So that's one thing I wanted you to note. Fine. And we are saying that all the regression models are used to predict the means, okay? But situation, and it means that there are certain parametric assumptions. And mostly when the dependent variable is normally distributed, it kind of helps you to get a good fit. Although it's not really a requirement. It's not really a parametric assumption. Most of the parametric assumptions are about the regression residuals or the error term, that the error term must be normally distributed and so on, but not necessarily the dependent variable. But if the dependent variable is normally distributed, it helps. The reason because the dependent variable is expressed as a function of the error term. So it means that technically, if the error term is normally distributed, any linear function of a normal distribution should be normally distributed. So this is to say that if the dependent variable is normally distributed, it kind of helps you it helps you for the residuals to sometimes satisfy the parametric assumptions of normality. But that is not always the case. So situations where even after data transformation, you still didn't achieve normal distributed residuals, okay? And somehow the regression estimate or the regression, even the R square is very low, or let's say the model is poor fit. It's just because the data is non-normal distributed. Let's say the data is, especially data set from immune responses, okay? Those who are into proteomics or genomics and so on, most of the data set are often skewed. And whenever they are skewed, sometimes no amount of transformation makes the data to be normally distributed. Now look at something. If a data is not normally distributed, but after taking log transformation and the data becomes normally distributed, it means that that data is log normally distributed. It's just something I wanted you to note. So but a data can be normally distributed and its log transform also normally distributed. And the data can be non-normal, but certain transformation can cause the data to be normally distributed. In the case of a log, if log transformation results in a normal distributed data, that data set, the original data set, is rather non-normally distributed, log normally distributed. Fine. Now, quantile regression rather helps us to estimate specific quantiles of the data, not the mean. So it means means are estimated based on the classical regression models we've been talking about. That is why whenever you are talking about interpreting the regression estimate coefficient for a dependent predictor, you say that a unit increase in that predictor would cause the dependent dependent variable, if it is continuous, the expected value to increase by something. So you see, the expected value means the mean of the data to increase by a certain amount based on the regression coefficient. If increase if it is positive, and decrease if it is negative, fine. But when it comes to quantile regression, it helps you to rather consider predicting the median of the data if you set the quantile to be 50% or 0.5. And you can also use it to look at factors predicting the 25th percentile of the data. You can use it to predict factors predicting the 75th percentile of the data. And mostly those who do clinical trials, or those who are doing studies where the data is heavily not normally distributed and all the classical regressions are failing. Okay, and since they are failing, you don't want to predict the means, you want to predict the medians or other quantiles. And because you know median is less affected by outliers, so predicting the median would be what advisable in that case. And that is why when you are doing classical hypothesis testing, even when the data is not normally distributed, and that you cannot use the parametric hypothesis testing, you are then forced to now use the non-parametric test, right? So for instance, for independent test, the non-parametric version is Mann-Whitney test. And then for the ANOVA, the non-parametric test is Kruskal-Wallis. For repeated measures ANOVA, the non-parametric test is Fredman's test. All the non-parametric tests, they rather kind of test the median, not the means. Okay, fine. So quantile regression is just a way of predicting specific quantiles of the data, whether the median, whether the 25th percentile. You can even use it to look at factors predicting the maximum of that data, especially those who do extreme value analysis. You can actually use quantile regression to look at predicting factors, because remember, with the regression, you are looking at factors predicting the averages. So it means you can use quantile regression to look at factors predicting the medians, or factors predicting specific quantiles, the 25th percentile, the 75th percentile, even factors predicting the maximum value of the data or the minimum value of the data. You can use quantile regression for that. So that's the beauty, and it's much robust to departures from parametric assumptions. So that's just something I wanted you to note. For the spatial statistics, mostly those who are into geography, ecology, they make use of that, especially when they are interested in spatial distribution. Sometimes if you're looking at the spread of an infection over some geographic locations and so on, then that kind of analysis you can use. So those geostatistics is where you see the statistical analysis, and there's a map with some specific summary measures inside the map and all those kind of things. That's like the spatial statistics. And the Bayesian statistical methods, I don't want to talk much about it, but the only take-home message is that the Bayesian is not a statistical model. It is just a method of estimation. All the classical statistical methods, or all the classical methods I've mentioned, most of the time, the parameter estimation is done either by method of least squares, method of movement, or mostly by maximum likelihood. That is if you know the likelihood function. But Bayesian, so it means the frequentist way of estimating parameters assumes that the parameters are constant. But Bayesian assumes that the parameters we want to estimate are random variables. And because they are random variables, it means that we can get distributions of that parameter. And by getting distribution of that parameter, it means we can learn more about the data. So Bayesian statistical methods allows us to use certain prior information about the parameters. Okay, certain prior information, existing information in the literature, to improve our parameter estimation. So you use the existing information about the parameters in the literature. If you don't know any existing information and you still want to use Bayesian, we use something called non-informative priors, and combining that with something called the likelihood function. The likelihood function is just the probability distribution of the data. And then based on that likelihood function and the prior, it produces something called posterior distribution. Now, when you get the posterior distribution, the average of the posterior distribution is just the parameter estimate. So it means Bayesian statistical methods are basically, the statistical methods here are all the statistical methods you are aware of. Just that if the method of estimation applies Bayesian estimation technique, then it gives a different name to it. But remember that not all the the only instance you can use classical Bayesian approach is when you know the exact likelihood function. So it means anytime you can implement maximum likelihood, you can implement Bayesian approach, the classical Bayesian. But there are instances you cannot evaluate, or the likelihood function is mathematically intractable or computationally expensive to evaluate, or you can't even write down the closed form, and it introduced something called approximate Bayesian computation. So in one of my papers here, this particular paper, you'll be exposed to a certain method of estimation called approximate. It's called approximate Bayesian computation, which is used in doing instances where the likely function is either mathematically intractable or computationally expensive. So I'll end here with the first session. The last session, remember, is just going to be 10 minutes and I'm done. So at this point, if you have any question, I think I should take a question now because people are tired. So do you want to ask me some specific questions if you have, and then we would proceed? Because we've spent a huge amount of time already, I'll just spend the last, because we started at 11, right? So we've literally spent 2 hours on just this. So what that means, I'm just going to spend 10 minutes, just 10 minutes on the last part, and then we are done. So should I continue the last part in 10 minutes before taking the questions, or I should take questions now?
No.
Okay. Should I finish first and take the questions?
Yeah, I would
No,
suggest
you have
that
to take some water. You are tired.
Yeah, I'm actually tired, but it's fine.
No, take some water first so that we mobilize our small questions, then we give to you.
Okay.